So in section 3, we're going to be talking about isotopes. Remember, we said, according to Dalton, not all the atoms are, well, according to Dalton, all the atoms are identical, but we know today that that's not true. So we're going to talk about that and talk about what isotopes are in terms of atomic and mass number, and then also determine protons, neutrons, and electrons. And this is really going to be a bulk of the test, knowing how many protons, neutrons, and electrons different isotopes have. And then eventually, probably tomorrow, we'll get to the mole, talk about Avogadro, and solving problems of that nature. So let's first go to atomic number. Just like we all have our own social security number, atoms of an element have a certain number of protons, and only atoms of that element will have that number of protons. So for instance, copper has a particular number of protons, chlorine has its own number of protons. There's a special number, or a name for this number of protons. It's called the atomic number, because that's the identity of the element. So every atom of copper would have the same atomic number. So you can see here, I have what you might find on a periodic table of the box for oxygen. The integer that you see on there is the atomic number. The decimal number is going to be your atomic mass, which we'll talk about toward the end here. And eventually we'll learn what the bottom thing is too, but that's for later on, a couple chapters down the road. For now, all you need to know is that the atomic number matches the number of protons. So if oxygen has an atomic number of 8, we know that oxygen has 8 protons. It just happens to have 8 neutrons and electrons as well. We'll get to that later. But isotopes are atoms of the same element that have a different mass. And if we go back, what would be causing that different mass? If it's the same element, we go back to here. What do you think? Could it be the electron? Could it be the electron that is making it have a different mass? Do you think the electron is changing its mass? If I add more electrons, what's the mass essentially of an electron? Yeah, we're not looking at the charge. The mass is not going to add anything because it's essentially 0. How about the proton? Can I have the same atom but with different number of protons? Remember, the protons are the identity of the atom. Exactly. If you have different number of protons, you have a different atom, a different element. So the only thing that can really change in a meaningful way is the neutrons. And that is the definition of an isotope, by the way. It's an element that has the same number of protons and electrons, but a different number of neutrons. And most elements in nature are going to be consisting of a mixture of isotopes. So you might have some oxygen atoms with 8 neutrons, and you might have some oxygen atoms you're breathing with 6 neutrons. It just depends on the individual atom, and you have a mixture of all the different isotopes. So there's a lot going on here. I need to clarify something because this picture is actually showing the atomic mass, which is an average of all the atomic of all the mass numbers. But the mass number is just an integer. Anything that ends in number, when we're talking chemistry here, the atomic number is an integer. The mass number is also an integer. And for oxygen, here, we've got 8 protons and 8 neutrons. You add them together, that gives me the mass number of 16. So all the mass number is the total number of protons and neutrons. Now, like I said, there's a mixture of all the different isotopes of oxygen. And when we average them all together, that's going to be what gives us this uglier number, the atomic mass. And we're going to learn how to calculate that at the end of the lesson here today. Any questions on that? So we have the oxygen with the 8 protons. This particular isotope of oxygen has 8 neutrons, making its mass number 16. And then 8 electrons. We know it's got 8 electrons because it's neutral, and the protons and the electrons are going to have to cancel each other out. So let's talk about a couple different notations with isotopes. We have hyphen notation, which is the way I say the isotope. Like if I have an isotope of uranium-235 or uranium-238, I'm going to write that out with the element name dash the mass number. So for instance, that oxygen isotope would be oxygen dash 16. So I'm going to write I'm glad you got to hear that. So it's oxygen dash 16. And then if for uranium-235, the 235 comes from the particular isotope. And then where'd the 92 come from? If we look at the periodic table, the 92 is the atomic number. So how we write that in nuclear form is we put the mass number on top, the 235 on top, and the atomic number on the bottom. I'll show you that with oxygen. It's a little simpler. We would do oxygen. Anybody know oxygen's atomic number? It's on the previous. Well, 16 was the mass number. Did not mean to zoom in like that. Yes. So 16 was the mass number. 8 was the atomic number. What's nice about this is it just kind of inadvertently gives us a subtraction problem. So if I want to know how many neutrons an element has, or an isotope has, I'm just going to take 235 minus 92, get a 3, get a 4, 1. So this would tell me that uranium-235 has 143 neutrons, and oxygen-16 has, like we said, 8 neutrons. So if you ever need to figure out the number of neutrons, because the mass number is protons plus neutrons, we can take the mass number minus the mass number minus the atomic number. Questions there? So you can see that written out. The number of neutrons is found by subtracting the atomic number by the mass number. And another, you might hear this word nuclide for a specific isotope. So if I'm talking about like the chlorine 35 nuclide, I'm talking about specifically that isotope of chlorine. So let's look at a sample. Speaking of chlorine, must have it in my head for that reason. How many protons, neutrons, and electrons are there in chlorine 37? First of all, does anybody know how to find the number of protons? Yeah, I like that. digging out your periodic table, because you will find that right on there. You got it. 17. And the reason I know that, for those of us online here, you can go to ptable.com. You see chlorine, and there goes my PowerPoint, but you see chlorine has an atomic number of 17. The mass number for the number of neutrons, remember, this is an average, so that's not going to help me right now. Yeah, argon would have a atomic number of 18.
So it's basically just in order of numbers.
It is, yeah, the periodic table. That was a question on the last test. The periodic table is in the order of atomic number. So I'll write that again. Protein is 7, or protein, I'm teaching bio here. Protons is 17. Neutrons, remember, we can take this number. You got it. You can write it as 37 with 17. And then my number of neutrons is 20. And in electrons, it's a neutral atom. So for now, just realize that the electrons matches the protons. So these homework questions are going to get a little repetitive. They're going to ask you the atomic number, the protons, the electrons. For now, they're all the same thing. Later on, we'll learn that electrons can be different in different ions, but for neutral atoms, atomic number, protons, and electrons, you should have three things that are the same. Amen.
So for neutrons, you're basically just subtracting 17, or the protons from whatever the dash number is.
Yeah, and that dash number is the mass number. So you're just taking away the protons from the mass number, which is the dash 37. Good stuff. So we already kind of said this just now. The atomic number is the same as the number of protons. You got it. And then you can tell me this one. How many neutrons are present in an atom of tin? We've got an atomic number of 50 and a mass number of 119. Yeah, so we take 119 minus 50, and we get 69. So then we have the relative atomic masses. And we talked about this yesterday, but the carbon-12 atom, what they did is they probably weighed a lot of carbon-12 and then divided that up to figure out how much one atom of carbon weighs. And then they took that carbon atom and divided it up into 12 to get the AMU, because you can't really just take a proton and put it on the scale. They do have the big accelerometer in Europe that they're testing particles with, so I'm sure they've isolated a proton and somehow calculated the mass. But this is how they do it in the standard scientific units. And then so carbon-12 is kind of like the standard, how we have a standard kilogram. The rest of the atoms are weighed, their weight is based on the carbon-12 standard. So let's talk about average atomic masses. These are two elements of helium. Two isotopes of helium. Let me get my terminology correct there. Two isotopes of helium. And in this one on the left, it's helium-3, meaning that because helium has two protons, helium has to have one neutron. The one on the right has two neutrons because, again, helium has to have two protons. So if it's helium-4, 4 minus 2 is 2. So those are two examples of isotopes of helium. Now let's just say, for argument's sake, I don't know the exact percentage of each, But if you had a helium balloon filled with helium, let's say that in nature 1% of helium is this one, helium-3, and 99% is helium-4. Would you expect the average atomic mass to be 3.5, right in the middle? If 1% is helium-3 and 99% is helium-4, what would you expect the average to be? Would it be right in the center, 3.5? I see no. You think it'd be closer to the 4 or closer to the 3? Like if I had 1% of helium, 1% of helium was helium-3 and 99% was helium-4. Yeah, you'd see probably something like 3.99999, right? And that's why we look at oxygen, that oxygen's atomic mass. It was 15.9994. What would you expect the typical oxygen atom to probably look like? What do you think the mass number of a typical oxygen atom would be based on this average atomic mass?
You can barely see that.
Yeah, the blue number is hard to see, but it would be probably 16 because it's so close to 16. But there is a way to calculate that, which we're going to look at here. We call this the average atomic mass. It's the weighted average of all the atomic masses of the naturally occurring isotopes of an element. And it depends on two things. It depends on the individual masses of the isotopes and how abundant they are. So like I was giving you with the helium, I just made up numbers, but 99% to 1%, that would be a relative abundance of the helium. So the example problem I have involves copper 63 and copper 65. So copper 63, lo and behold, basically has a mass of 63. They gave us the exact to 8 sig figs. But really, copper 63's mass is 63, and copper 65's mass is 65, but they gave it to us in 64.927794 AMU. For abundance, let me turn that into a percentage because we're going to do a calculation with it. So I'm going to change 69.15% to 0.6915. And I'm going to change 30.85% to 0.3085. So what's going to happen is this mass is going to contribute this percent, and this mass is going to contribute this percent. My grades in chem are like that, where you get a weighted percentage of your grade, where tests are 60%, and labs are 30%, for instance, or 20% rather. So you can see that tests are going to be weighted more. They're going to have more weight in your grade than labs are going to have. In the same way, because copper 63 is more than twice as abundant than copper 65, what do we expect that mass to be closer to, that average to be closer to, the 63 or the 65? We've got 69% is 63 and 31% is 65. Yeah, it's probably going to be closer to 63. So let's test this out. What we're going to do is we're going to multiply the mass times the abundance for each one. So let me go and get my calculator. As long as PowerPoint doesn't crash on me again. And oh, wow, look at that. The numbers are already typed in for me. So 62.929601 times 0.6915 gives me 43.5. So this is essentially the contribution to the total average. So 63, that's its contribution. 65 comes out to 20.03. So 43.52. 43.52 was these two multiplied together, and 20.03 was these two multiplied together. I add those up, I get 5, 5, 3, 6. You said it'd be closer to 63, right? Looks like you were correct. And that's in AMUs. So 63.55 is the average atomic mass. So what we did was we took each one's mass times its abundance, and then we added those together. You could have two elements like this one, or two isotopes like this one, 3 isotopes, 4 isotopes, but you're just going to multiply the mass times the abundance and then add them all together. Any questions on how I got that 63.55? So one last little tidbit of information. I just did all that math to find the 63.55. Where else could I find it when I look at copper? Look at that. Mass, average mass of copper, 63.55. So you can always, these are nice because you can sort of luck into the correct answer. Because you should be getting, unless you're rounding, you should be getting what's on the periodic table.